All right, on the 3.2b worksheet, a question was asked about problem number 2. So it's a piecewise defined function here, and I've asked you guys to come up with the derivative of the piecewise function, and then more importantly, talk about whether the function is differentiable at its seams here. And I'll bet some of you had trouble right off the bat just coming up with the graph of this thing. So let's see what we've got. One of the things that I wish you guys knew a little bit better than it seems like you do these days is how to graph a quadratic function out of vertex form. And that's the way that the first two lines, here and here, of this piecewise defined function are given to you. So your h and your k right here, guys, for the first part, h is the number being subtracted from x. So our vertex here is going to be at -6. Okay, because that's the opposite of that +6 there, and k is the value at the end, +6. So we've got a vertex to this parabola at -6, 2, 3, 4, 5, 6, and then +6 right up here. Okay, now what else do we know? We know that this parabola opens downward because it's got a negative a value in front, but that a value is 1. So with a regular size parabola, it's not fat, it's not skinny, opening downward, we would go right 1 and down 1 right there. We'd also go from the vertex now right 2 and down 4, because 4 is 2 squared, and that gets us, I believe, to what would be the endpoint of the first part of this graph. When x is -4, which I'm using right here, let me just check this real quick. -4 plus 6 is 2. Squared is 4. The opposite of that is -4 plus 6 is 2. So yeah, that's where we're at. This thing ends at the point 4, 2. Now I see I made one mistake, but I'll fix that in just a second. So the parabola kind of looks like this, and it does the same thing on the left-hand side. So that would be the first part. Now the mistake that I made, I saw as soon as I did it, this inequality right here is just x is less than 4, which means this actually should have been an open dot right there at the point -4, +2. Although in a lot of cases, that ends up being a moot point, but again, I don't want to assume. Okay, this is getting a little sloppy, so let me clean some of this stuff up. Let's focus on the second part of this piecewise defined function now, right here. Once again, that is a quadratic function, and it's in vertex form. And your vertex there, the h value right here would be -2, and the k value is -4. So -2, -1, 2, 3, 4, our vertex would be right there. And now again, this is a parabola, but this one opens up, but its a value is 1. So I would go left 1, up 1, and put a dot right there, left 2, and up 4, and I would get a dot right there. So I think this thing actually begins at the point -4, 0, but it's not a bad idea to check that by plugging a -4 in right here. -4 plus 2 is -2, squared is 4, yeah, -4 is 0. And that should be a closed dot because of the or equals to there. So this is what the left side of that parabola looks like. Now for the right side, it goes all the way to x is less than 0. So what happens when we put a 0 in there? 0 plus 2 is 2, squared is 4, -4 is 0. That ought to be an open dot then at the origin at 0, 0. So there's the middle part of this graph. And the last one now, shifting gears, isn't a parabola at all. This last part is just the square root of x that begins when x is equal to 0. Put a 0 into the square root of x, and you're going to get 0, a closed dot. So this closed dot at 0, 0 fills in the open dot that we had from the second part. And a square root function is the top half of a sideways parabola, and it looks something like that. So all of that work there, guys, is going to get us just our graph. Now, what's next? We were supposed to come up with the derivative here and see what we've got. So the derivative of the first part right over here, this is not my best question, guys. It kind of requires a concept that I haven't really taught you guys yet, so sorry about that. But if you want to take the derivative of the first part, treat this x plus 6 as just one big base, and let's do the power rule. That 2 on the exponent gets multiplied by the -1 out in front, and we get a -2. We leave the base, x plus 6, the same. We drop the exponent by 1, so the 2 becomes a 1, which I don't really have to write at all, so okay. And technically with the chain rule, you multiply by the derivative within, but the derivative of x plus 6 is a 1, and there's really no point in writing that. Then the derivative of the plus 6 at the end is a 0, and there's no point in writing that plus 0 there either. So guys, that's the derivative for all values of x that are less than -4. On to the second part. Boy, this really did get ugly right here. Okay, on to the second part now. Ooh, there you go. Let me do that same trick. I'll bring that 2 out in front, and we'll get a 2 times the same base, x plus 2 to the first power minus 0. So that's our derivative when, now, I'm not doing this on accident. This is on purpose, everybody. -4 is less than x, which is less than 0. And you probably want to yell at me right now and say, wait a minute, that was less than or equal to, so you should have written that. No, I left that out on purpose right now, and that's because I don't know yet whether or not the derivative exists at -4. Actually, I do know from the graph, but I'll get to that in a minute. So maybe I'm going to come back and change this to that same symbol right there. Maybe not. I'll come back to that in a minute. And now for the last part, the derivative of the square root of x. Remember, guys, that that's x to the 1/2 power. So its derivative would be, let me write this down on the bottom here, 1/2 x to the -1/2 power, which would be more cleanly written as, there's your 1/2, and x to the -1/2 becomes a square root of x on the bottom. So 1 over 2 root x. And that applies when x is greater than 0. Now again, same discussion. Maybe greater than or equal to, but I'm not sure yet. So I'm going to leave it blank for now. Hopefully you'll see what I mean in just a second. Now, the two seams of this piecewise defined functions are where the different parts come together. So we've got a seam right here at -4, and we have a seam right here at 0. So those are, I'm going to switch colors here. We'll go purple here. My first seam is at x equals -4. Second seam is x equals 0. So two questions, just trying to help you guys remember what it is you need to check here. Is this function continuous at x equals -4, which is right here? And I'm hoping you guys can look at this and tell me quickly that the answer is no. Now, the reason for that, everybody, is that your left-hand limit, in fact, let me write this out, just abbreviate, left-hand limit as x approaches -4 from the left is 2, but the right-hand limit as x approaches -4 from the right is 0. Now, I'll tell you right now that if you have a good, careful graph drawn, you don't have to give me this information right here. I'll let you use the graph as evidence of continuity or lack thereof, but your graph had better be right, guys. Let's keep that in mind. Now, as soon as we see that the function is not continuous, then automatically the answer here for differentiable is a big fat no, and you do not need to test the values of the derivative here at x equals -4. Because if the function is not continuous, there is no way that it's differentiable. Remember that our definition of differentiability had two conditions with an and in the middle. And as soon as one of those is ruined, then you don't have a derivative at that spot. So don't bother checking the left and right hand derivatives at -4. It doesn't matter what their values are. Now, how about the second seam? At x equals 0, we ended the first part of the graph at 0, 0, and we began the second at 0, 0. And because of the greater than or equal to, we filled in that dot right there. This one is going to be a yes. Now, the reason why, if I wanted to write this out, my left-hand limit as x approaches 0 from the left is 0. My right-hand limit is 0 also, and f of 0 is equal to 0 as well. So that's the three-part test for continuity at a point. Left-hand limit, right-hand limit, and the value of the function itself all have to agree, and they do. So now that we have continuity, now we need to go over here to test for differentiability. And to do that, we need a left-hand derivative, and we also need a right-hand derivative, and we need to find out if they're the same or not. So now for the first time, we need to take a look at what's going on right here in f prime of x. And for this spot right here, when x is 0, it's going to be the second and the third parts of the piecewise derivative that we have to look at here. So for the left part of that, that's going to be the 2 times x plus 2, which we'll evaluate when x is 0. 0 plus 2 is 2, times 2 is going to be 4. Got it. And the right-hand derivative then, is 1 over, sorry, I kind of wrote over that, 1 over 2 root x. And if we were to evaluate that expression at x equals 0, I think you guys are going to find very quickly that that becomes a 1 over 0, which is undefined. And I better write that right here. So what have we shown here, guys? At x equals 0, the left-hand derivative and the right-hand derivative do not agree with each other. So this answer is a big fat no here as well. So we actually have this piecewise defined function with two seams, and the function is not differentiable at either one of them, but for two different reasons. For the first part right here at x equals 4, the derivative didn't exist because the function was not continuous. And at x equals 0, the function was continuous, but the left and right-hand derivatives were not equal to each other, and that's why there was no derivative at 0. So a lot of ideas going on in that problem. That's how we handle the 3.2b worksheet, problem number 2.